YouTube?
Now it's live, sir. Ma'am, now it's live.
Ravi, sir, please make this.
Rajesh, I could see my slides.
Yes,
It's available.
we can
Yes, we can
see your
see.
slides.
Hello,
Sir,
Vani.
we have
We can see your
Okay.
slides.
Hello, tell me, how are you?
first, sir.
Good morning.
Rajesh,
Yesterday I could not. Yesterday I not.
Okay, so we are live now, everybody. So, good morning, Professor Hegde. So,
Thank you.
today, Professor Hegde will continue his talk on graph labeling and data application. So, please, Professor Hegde, please continue.
thank you, Rajesh. Good morning, everyone. Yesterday, we had some discussion or some information regarding the origin of the graph labelings, the origin of some other problem because of the graph labelings were originated, and some developments, and the recent development regarding the original problem. Okay, so today let us start with some quantitative analysis of the papers on graph labeling problems. As you all know, the basis for, or the basis from which you can have, or we can make some analysis, is the Gallien's survey paper. It's a big basket full of information. Of course, there is some redundancy regarding the notations and the graphs, because people started defining their own graphs and giving their own names. Normally what Gallien does is, he will ask your paper without your copy of the paper. He will not include your reference, and he will make a summary of the paper and simply put it in that basket. Definitely it's a treasure, but at the same time we have to be little careful while going through it. So for my quantitative analysis, the basics or reference is Gallien's paper. See, we all know the labeling problems originated in from the conference in 1963, but not much work on labelings were done because of labelings, but work was done because to solve some other problems. The first version of Gallien's survey.
Sir, slide ಬರ್ಬೇಕು ನಿಮ್ದು.
Pardon?
Please share your slides.
This is the slide, no? I'm
Only good morning slide is there.
yes, only good morning slide only I'm using now.
Okay, fine then, fine. Sorry.
Okay. Yeah, this is some introduction I'm doing. Okay. So the first paper on dynamic survey appeared in the year 1998 in the same journal, in the sense Electronic Journal of Combinatorics. So let us see what are the quantum of papers published after that. Okay. See, in the year 1998, the number of pages in the paper were 46 in the Gallien's survey paper, and there were 305 papers referred that included preprints, reprints, etc. Okay, next year the number of pages increased to 10 more, and there were 378 papers referred. So you can see in 2000 it is 412, 2001 it is 513, 2002 it is 572. So like that, around 2010, it was 1,198. The intervening years, that 11, it is 1,329, 12, 1,460, 13, 1,700, 14, 1,900, something like that. In the latest survey, in the 2020 version, the number of pages increased from 46 to 553, and number of papers increased from 300 plus to 2,922, approximately 3,000. Okay. Now, if you look at this, how nice the curve looks. Steady, and like the growth is also not very fast. It is not from 1,000 to 3,000 in 1 year or like that. Okay. So this gives an idea that more number of people are interested and working on graph labeling problems, as I told earlier, maybe because of the applications or logico-mathematical. But only thing is, what we can analyze is the number of applications have not been increased so much. So this shows that mainly it is intrinsic use of mathematics or logico-mathematical. And what I observed in the papers is that some of the papers published in 1990, also they quote the reference of Gallian survey in the papers published in 2019 also quote the papers published in 2010. So this is for the researchers. So kindly update your references and quote the latest one. Of course, on graph labeling problems, there is no problem because this is a free access journal. Okay. And definitely it is difficult to go for qualitative analysis. Only one thing what we observe here is the results on or results involving the structural properties are comparatively very less compared to the number of papers on the special classes of graphs and giving the labeling in trial and error method. But there are papers, one can see that it uses the idea of other branches of mathematics, and because of such things, at least few papers appeared in good journals. So that is why the need of the hour is intradisciplinary. Afterwards, it is interdisciplinary. So kindly think of collaborating with people working in other branches like algebra, number theory, etc., even linear algebra, and try to produce good results which will be published in good journals. Okay, so with this I'll go to the application part. As discussed yesterday, we know that the labeled graphs are applied in X-ray crystallography, radio astronomy, coding theory, etc. And also we know that the labeled graphs are used to solve some problems in linear algebra, to some problems in geometry, and to solve some problems in other branches of mathematics. So we will discuss some application, one application in real life, that is X-ray crystallography, and maybe another application in geometry, if time permits, some other applications. Okay. To start with, ambiguities in X-ray crystallography. Determination of crystal structures from X-ray diffraction data has long been a problem of the crystallographers. the ambiguities inherent in this procedure are now being understood. So the papers of Patterson, Franklin, Bloom will discuss on the ambiguities. These are some of the papers in X-ray crystallography. I have mentioned these papers because in today's talk, we will have the reference for these three people. That is first application. And another application is construction of polygons of same internal angle but distinct sides. So using the strongly k-indexable labelings of a cycle C2n+1, we can construct a polygon of sides P4n+2 such that the internal angles are equal and lengths of the sides are distinct. So here is a reference. It's a paper of myself and Sudhakar Shetty. In this paper, Strongly Indexable Graphs and Applications, published in Discrete Mathematics, we have discussed this application. Another application is solution of linear congruences. Myself and my student Srinivas Murthy, we have published a paper in National Academy Science Letter. It's a partial solution to linear congruence conjecture. And there is another application which we have not discussed so far. This is characterization of sequentiable groups, complete mappings, neofields using the graceful labeling of directed graphs. So using the graceful labelings of directed graphs, these algebraic structures are characterized. So if one is interested, you can go through the paper by Bloom and Su on graceful directed graphs published in Siam Journal of Algebraic and Discrete Methods in 1985. But now this journal, the nomenclature has been changed. This journal, Siam Journal of Algebraic and Discrete Methods, has been renamed to Siam Journal of Discrete Mathematics. Okay. Now we discuss some applications in detail. You can refer another paper by Bloom and Su on graceful diagraphs and problems in communication network addressing. Okay. Now let us discuss in detail about the ambiguities in X-ray crystallographic analysis. Okay. Normally, or sometimes it happens that distinct crystal structures will produce identical X-ray diffraction. So what is the ambiguity? Once they know, because normally what they do, they identify the crystal using the X-ray diffraction pattern. But it was not known whether this X-ray diffraction pattern was due to the crystal A or crystal B. That was the ambiguity. Okay. These inherent ambiguities in X-ray analysis have been studied by Picard, Patterson, Franklin, and Bloom, as mentioned earlier also. Extensive results for the case of an infinity of points have been studied by Patterson, and the case of finite arrangements have been studied by Picard, Franklin, and Bloom. See, as I quoted earlier also, so we will be using these three references in our discussion. See, normally, nowadays, what we talk about, input, then processing, and then output. Okay. So in this crystallography problem, what is an input? A crystal. Okay. And it has to be processed. That means what we want is X-ray diffraction pattern. Okay. So here the processing means it's a diffractometer. And output is X-ray diffraction pattern. Now let us see how we can relate these two graph labeling problems. What is happening in the practical problem is that a crystal, for example, is a diamond. A crystal is put into X-ray diffractometer to get the X-ray diffraction pattern. In the sense, or what this diffractometer does, once the crystal is submitted or given to the diffractometer, it identifies the atomic positions of this crystal. Okay, the atomic positions of the crystal, and measures the interatomic distances. That is, first fixes the positions and then it measures the difference between each atomic position. Okay, and gives the output as X-ray diffraction pattern. Now, so input is a crystal, but what is an output? Set of numbers. What is these numbers represent? The interatomic distances. Okay. So ambiguity is, suppose you are given the output, it is just a set. Now, using this set, can you say whether it's a diamond or some other crystal? That was the ambiguity. Now, how we can put this into mathematics? For us, it is set of numbers. That is, crystal means the atomic positions are fixed in the crystal. So we are taking those positions as the set of numbers. And what we do, processing, we find the absolute difference of the set of numbers. All absolute, all pairs, that is, if there are n, choose 2. We find the absolute difference of the set of numbers and get output is again a set of numbers. So this is how the real life problem in X-ray crystallography can be related to numbers. Okay, now how we can relate this to graph labelings? So we take a graph and give numbers from this set. We take a complete graph. One example, it's not necessary, it depends upon the structure. Suppose we take a complete graph with n vertices and we take a set with n numbers and find the absolute difference of the values of the vertex numbers and get back as output as another set of numbers. Okay. So now the problem is clear that we are taking a graph, we are taking a set, and we are defining a rule, and we wanted the output. Okay. As I told, it's already. We know that in some diffraction, information may correspond to more than one structure. This problem is mathematically equivalent, as I discussed, determining all labelings of the appropriate graphs which produce pre-specified set of edge numbers. Now, one problem here is, I told you, we take a set of numbers, we find the absolute difference, and we get another set. Now, the possibility in the output set is, suppose you take the set as input, the output may be your multi-set. That means there may be repetitions, or there may not be repetitions. Okay, fine. Now, physically determining the sets of atom positions that are homometric to determining the vertex number sets results in the pre-specified set of edge numbers. This is the problem. Here the word homometric is there. Then let us see what is Okay, that's what we have discussed, I told. Oh, sorry. Yeah. Now, Franklin studied finite sets of points that would give same diffraction pattern. He called these sets strictly homometric. Now, what he wanted to prove that take two sets, he calls this homometric, and to find the absolute differences of all the numbers in the set. His question is, can we get the same diffraction pattern from these two sets? Okay. Now, why he defined homometric? See, if the sets are not homometric, then even though both the sets will give same diffraction pattern, the crystallographer's interpretation is, if two sets may produce same diffraction pattern, but it is not necessary that it is because of two different crystals. It may be because of the changing the positions, that is giving the rotation of the same crystal, giving oscillations for the same crystal. So they said that such problems are not interesting. So he wanted to show that, okay, these two sets are not the rotations of one set. So he defined a homometric, the pair of homometric sets. And he defined two sets, R and S are said to be homometric if S cannot be obtained from plus minus R plus some constant, and the distance sets D of S equal to D of R. He says two sets are homometric if one cannot be obtained from the others using this operation, but the distance sets are the same. Okay. Let us consider. So for us, R is 0, 1, 4, 6 and S is 0, 2, 5, 6. These are two different sets. Okay, not distinct, but different sets. Now let us find the set of all distances using S. So one can see that 0 to 2 is 2, 0 to 5 is 5, 0 to 6 is 6, 2, 3, 3, then 2, 4, 6 is 4, and 5, 6 is 1. So this is ds. Similarly, we can see that dr will give the same set. Now, the question is, are these sets homometric? Can S be obtained from R or vice versa? Now, let us take this minus R plus 6. What is that? Minus R is 0, minus 1, minus 4, minus 6, plus 6. So that is 0, 2, 6, 5, which is nothing but yes. So even though they are two different sets and produce the same distances, but they are not homometric. That means one can be obtained from the other. So this is not an example to show that two different crystals will give the same diffraction pattern. Okay. Now consider this set, these two sets R. It is 0, 1, 3, 4, 5, 7, 9, 10, 12, and 0, 2, 3, 4, 6, 7, 9, 11, 12. Definitely these two are different sets. But are they homometric? Then we'll see. Now we'll find that set of distances in R, dr. In fact, I would have defined this earlier. Okay. Is the set of all absolute difference of A minus B such that A, B are in R, and D of S equal to absolute difference of C minus D, where C, D are in S. And you see that this is the set D of S. This has 36 elements. Okay, because in the set there are 9 elements. 9 choose 2 is 36. We have 36 elements. And one can verify that you cannot make or you cannot obtain one set from the other. So that is why these are homometric sets. So R and S are homometric, but both produce the same distance set. So Franklin claims this is an example to show that two different crystals represented by R and S will produce the same diffraction pattern. So that is why just by taking the diffraction pattern, you cannot say that which crystal produced it. That is, there is an ambiguity. Now what we observe here is, even though R and S are homometric and the distance sets are the same, what we observe here is there is a lot of repetitions of the same numbers. So this is a multi-set. Okay. The sets and R and S are sets, but the output is a multi-set. Now, this was presented to the crystallographers, but they did not bother too much because they said that there are a lot of differences. Now, so these two are complete graphs with 9 edges, 9 points and 36 edges, and whatever the sets R and S you had, we have given the labels to this K9 using R and S. So what we say, display of each of these two 9-element homometric sets is done with complete graphs with 9 vertices. So these vertices are labeled by the elements of the set and the edges with different set. So this is how the graph labeling problem comes into or comes here in the problem of X-ray crystallography. Okay, let's proceed further. Now what we know is that there are two different crystals which can produce the same diffraction pattern, but there is a repetition of numbers. Okay. Picard presented a theorem which crystallographers immediately accepted because of its narrowing of these necessary scope for their investigation into diffraction pattern ambiguities. See, as I told earlier, the X-ray crystallographers, they said there is a lot of repetitions. Now what Picard said, or it was believed that Picard had proved if all the elements in the different set are distinct, that is input is a set and output is a set, there is a unique set that would generate it. So it was believed by the X-ray crystallographers that if all the elements in the output are distinct, then that is due to a unique crystal. And in fact, it was believed that Picard had proved it. Okay, let's see what happened next. So what they believed is no pair of homometric sets was believed to exist with differences comprised of distinct elements. So this was believed by the X-ray crystallographers. See, as we can see, Franklin's construction of homometric set do not violate this condition, since his different sets always include repeated elements. That means this is not a counterexample to Picard's theorem. Okay. Bloom has proved that this theorem was not true by producing many pairs of homometric sets, that is, many counterexamples to Picard's theorem. Okay. Consider the set R 0, 1, 4, 10, 12, 17 and S 0, 1, 8, 11, 13, 17. So both have same number of points. And let us take D distance set. D of R is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 are missing, 16, 17, and which is equal to D of S. And definitely one can, one can verify that these two are homometric. Okay, so this is the smallest counterexample to the Picard's theorem, and it was also proved that if you take here there are 5 elements set, there does not exist a counterexample. The minimum counterexample will have 2 sets having 6 elements. Okay, this is the counterexample produced by Bloom and Golomb for Picard's theorem. Okay. See, and that was an example, and they produced the sets like this: 0, u plus v, 4u plus 2v, 6u plus 2v, and 8u plus 2v. This is one set, and this is another set. So this was the original counterexample which we have seen before, is obtained by setting u equal to 1 and v equal to 3, and all choices of u and v results in sets of distinct differences. Okay, and if v is fixed at 3, each positive integer value generates a different counterexample to Picard's theorem. So these are the basic sets to produce the counterexample. They have produced so many counterexamples to Picard's theorem, thereby settling the claim that even if the X-ray diffraction pattern contains distinct numbers, there is a possibility of 2 crystals producing the same counterexample. See, in graceful graph theory, we can see that the complete graph with 5 or more points cannot be gracefully labeled. That means Kn for n greater than or equal to 5 is not graceful. See, most of the time what we do, if we want to prove just a result, we just leave. We prove that a complete graph Kn is graceful if and only if n is less than or equal to 4, then leave it. But Bloom and Golomb, they did not leave it there, and they wanted to know how well you can label the large graphs on n vertices. Okay, this led to 2 theoretical directions. Each of these has practical applications. So what are those 2? See, we know that the complete graph with large n cannot be labeled using the labels from 0, 1 to 2 number of edges, so that all edge values are distinct. Now here we can think about, or they thought about 2 different directions. One is, I don't want all the numbers should form a set of consecutive numbers, but I want it to produce the set of numbers, a set having different numbers. That is one thing. Second thing, suppose if I increase the maximum value, can I get the set of, can I get the different sets having all different numbers? Okay, and the direction taken by labeling the complete graph led to the constraint on the largest allowable vertex number which led to the counterexample of Picard's theorem. Okay, so in the counterexamples, they have increased the number of maximum number, in the sense, in the first one, see, so here there are 6 points, but if you take a complete graph with 6 points, the maximum number of edges is 15. Okay, but according to the graceful labeling, it can go only up to 15. So they know that if you have only up to 15, you cannot give. So they have used the number from 15 to 17. So that is one direction, increasing the maximum number. Okay, yeah. Yes, sorry. Yeah, the second direction is finding the maximal complete subgraph of a complete graph. Okay, using which we can labeling, or sorry, we know that in a complete graph there are n choose 2 lines. Using n choose 2 lines and using the constraint of graceful labeling, you cannot give graceful labeling. So what the thought is, you remove number of edges. They thought of finding how many edges are to be removed from a given complete graph so that the resulting graph is graceful. See, remember here, one direction is increasing the maximum number and finding the set of numbers in the distance set having all different numbers. Okay, that is increase the maximum number. Second is remove the edges from the complete graph such that the resulting graph is graceful. Okay, so now the first direction led to the counterexample for Picard's theorem. Now the second direction led to the limitations of communication networks. Okay, so in communication networks, they wanted the network to be graceful. Okay, if there are 10 points, then they wanted a network with 10 choose to 45 lines, but having all the labels of the lines distinct using the technique of graceful labeling. And the second direction, the application from the second direction is that Bloom and Golomb proved that you have to remove 1/3 of the number of edges from the complete graph to make the resulting graph graceful. So this showed that the knowledge of 2/3 of NC2 is the limit for the number of edges in a graceful graph. So this shows the design limits for communication networks with given number of nodes. Okay. See, this is a lesson for the young researchers that if we are able to prove that some result like this KN is graceful, we should go further to see that why it is not graceful and what best can be done using the similar ideas, that is complete graphs or increasing maximum number or removing the number of edges. Okay. Now we will go to, I think only I have 5 minutes. Another application takes at least 15-20 minutes. So what can I do? Can I stop here? Yes, organizers.
Is there any application which can be covered in 5-10 minutes?
Yeah, 5-10
Yes,
minutes.
sir.
Okay, I'll try to. I'll try to.
You try
Yes, sir.
this one, no problem.
Okay.
Okay, because 15 minutes we have to give to the students, and we
Yeah.
started about 10 minutes late.
Okay.
So we will
Yeah,
take,
that's why. That's why. Yes.
we will take the
Yeah.
time from the organizers to
Yeah.
extend. 10 minutes.
Okay. Now, so we have defined, myself and Dr. Acharya, a technique or labeling called strongly k-indexable labelings or strongly k-indexable graphs. So we have taken here the star as addition. An additive labeling f from the vertex set of a graph to 0, 1 to 2, number of vertices -1, such that the values of the edges f plus of g are all distinct. We call it as an indexer. So how the values of an edge is calculated? For any edge f of uv, the edge value is f of u plus f of v, just addition. Okay. Now that we call such labelings as indexable labeling, and a graph admitting such a labeling is called indexable graph. Okay. We have defined, or it is generalized, that a function f from 0, 1, 2 to p is called kd indexable if the edge values form an arithmetic progression like k, k plus d, etc., k plus q minus 1 into d. So here there is no restriction for, here the restriction is only they are distinct. Now, a labeling is said to be strongly kd indexable labeling if the edge values form an arithmetic progression, okay, k, k plus d, k plus qd, etc., k plus q minus 1 into d. A strongly kd indexable graph or labeling of G is when d equal to 1, we call it is strongly k indexable labeling. And if k equal to d equal to 1, we call it strongly indexable labeling. So we are going to discuss an application of strongly k indexable labeling. So the reference is Acharya and Hegde, strongly indexable labeling, published in Discrete Mathematics in the year 1991. Okay. What is the application? Here, we use strongly k-indexable labelings to construct polygons of different sides and equal internal angle. How? The construction of, we take a cycle C2n plus 1, and we know that the cycle C2n plus 1 is strongly k-indexable for k equal to n. Okay. So we take a strongly indexable cycle in graph theoretic sense. Consider a polygon, regular polygon, P2n plus 1, of course, regular polygon, and the lengths of the sides are equal. Then what we do, we give a strongly k-indexable labeling for that cycle or polygon. So now onwards, we will talk about polygon. Okay. So we take a polygon with sides P2n plus 1, and then we give a we give a strongly k-indexable labeling for that cycle, and then replace the vertex values by 1. Okay. And we denote the vertex u of the given polygon as I, because you know that the numbers are from 0 to p minus 1 in the k-indexable labeling, and the after replacement, the numbers will be from 1 to 2 number of vertices. Okay. So each graph, each vertex is labeled as I. Then what we do, we divide each side of the complete of this polygon into 4n plus k plus 4 elements.
Sir, your time is about to end, sir.
Pardon?
Your time is about to end, sir.
See, I have started as told. I have started at maybe 11:15.
11:10, sir.
Okay, no problem. We will
Okay.
take time from the
No,
participants.
I have started. It doesn't look nice to abruptly. I just give the outline.
Okay, sir.
Okay. So what we do, we divide each side of that regular polygon into 4n plus k plus 4 equal parts. Then we denote the point which is at I parts distance from the vertex vi as vij, if vj is adjacent to vi. Now, since vi is adjacent to two vertices, because we are taking the cycle or polygon, we take the points vij and vik on the edges, and we join the edge vi vj and vi vk. Okay, then what we do? Okay, sorry. Then we apply the similar procedure to all the vertices. Okay. From the above steps, we get P4n plus 2, and clearly each internal angle of the constructed polygon will be equal to 2n by 2n plus 1, 5. Okay. Then, so now what we have said, we have constructed we have taken a polygon of sides P2n plus 1, and by using the construction, we have constructed a polygon of with the sides 4n plus 2, double the number of sides. Okay. Now we have to calculate the lengths of the sides of the resulted polynomial and the internal angle. So definitely we know that internal angle is always 2n by 2n plus 1, 5. Now we have to we have to find the lengths. Let us see how we will find. Now there are two types of sides. One, a part of the original polygon. Another is a part of the constructed polygon. Okay. Now, if the lengths are the portions of the edge of the original, that C2n plus 1, then we find the new length as 4n plus k plus 4 minus I plus j, and otherwise we get the sides of the form square root of I square plus I square minus 2 I square cos of 2n minus 1 by 2n plus 1. If, as I told, if the sides is of the join of vi and vj, vij and vik. Okay. Or you can keep it or put it in the form it, where t is equal to square root of 2 times 1 minus cos of 2n minus 1 by 2n plus 1, 5. Okay. So we will just take the example and see. So here we have taken a triangle, okay, and a cycle now, and given the strongly one indexable, because it's of the form 2n plus 1, one indexable, that is 0, 1, 2, and the edge values are 1, 2, and 3. Okay. Then what we did, we have replaced this 0, 1, 2 by 1, 2, 3. And in this case, the 4n plus the k plus 4n plus 4 will be 9. Okay. That means we have divided this triangle, each side of this triangle into, you can see there are 9 parts. All are 9 parts. Okay. Then what we did, we have labeled the vertices as V1, because here it's 1, V2 it's 2, V3 it is 3. Then constructed the points V1, 2, because these are adjacent. V1, 3, these two are adjacent. V2, 1, this point. V2, V2, 3, this point. And this is 3, 1, this is 3, 2. And so we have joined 1, 2, 1, 3, 2, 1, 2, 3, 3, 2, 3, 1. So this is the constructed 4n plus 2 polygon. Okay. Now, as you can see, the internal angles are the same. And how we calculate the sides? If the sides of these sides are the part of the original triangle, then already we know that this is 9. Then 9 minus I plus j. I plus j is 1 plus 2. It is minus 3 equal to 6. So this portion, this is 6 units. And 9 minus 4, it is 5. This is the portion of this edge. This is 5 units. And 9 minus 3 is 6, 9 minus 3, 5 is 4. The length of this is 4 units. Now, how we calculate the length of these edges? That is using the formula as IT, you have no, that is IT, where T equal to square root of 2 times 1 minus, here cos 60 it is. Okay, cos 60. That is equal to, you will see that T is 1. So the value of this edge is 1T, that is 1. Value of this edge is 2T, 2 into 1, 2. Value of this edge is 3T. Thus, you see that the length of all the sides are distinct. Okay, I'll just give another example. This T1 is obvious. Now here in this case, if you take C5, here N is 2, and you can see the sides are 6, 7, 8, 9, 10, and the remaining sides are 1T, 2T, 3T, 4T and 5T, where your T is 1.6180 something. So like this, you can construct a polygon with different sides and same internal angle. So this is what we did using the strongly indexable labelings. So with this, thank you one and all. Thank you very much.
Thank you, sir. So any questions from the speaker? Okay, so we have one question from Priyanka. Yes, Priyanka, go ahead. Please unmute yourself and please ask your question.
Hello,
Priyanka.
sir. Namaste, sir.
Namaste.
Sir, myself Priyanka from Karnataka University, sir.
Yeah.
I'm having one query on this talk, sir. Sir, can it possible to do labeling for crystallographic structures like titanium fluoride and sodium chloride, sir?
I could not understand your question.
Sir, can it possible to do labelings for crystallographic structures like titanium fluoride, sodium chloride, those type of structures? Can it possible to do labeling, sir?
No, I don't know about your compounds. So
No, sir.
I just told you, because I don't know what is the structure of your crystal and other things.
Yes, sir.
Related the problem of X-ray crystallography,
Yes, sir.
the ambiguity in X-ray crystallography, how
Yes,
those ambiguities are
Yes, sir.
called or pointed out using graph labeling problems.
Yes, sir.
Expert in chemistry.
Yes, sir. Can it possible to apply? I am asking.
No. Here we have not taken a particular crystal. We have taken a general crystal.
Yes, sir.
Yeah.
Thank you, sir.
Okay.
Okay, sir. So we have one more question from some C. Santanaman.
Yes, please.
Yes, you can unmute yourself and ask your question.
Yeah, sir, we are having X-ray after
Yeah.
diffraction. How that we connect a graph and a set of numbers. Set of numbers is comes from where, and where is a graph? I have small doubt, sir.
See, here it is not the question of a graph or set of numbers and all.
Okay,
So here, what we are doing, or as mathematicians,
okay.
have shown that if you interpret the crystal if you take a crystal,
Okay, sir.
know the interatomic positions of the crystal, and what we did was those the atomic positions are taken as points.
Okay, sir.
We have taken the problem as getting a complete graph.
Oh, right, sir. Right, sir.
Okay.
Okay, sir. Okay, sir.
And giving the labeling to the complete graph so that the edge values are distinct.
Okay, sir.
Okay, I suppose you understood now.
Okay, sir. Thank you, sir.
Okay.
Thank you very much.
So, any other question from any other participant? Okay, so Shilpa Gokhare is there. Yes, Shilpa, please unmute yourself and ask a question.
Yeah. Hello, sir. Hegde, sir.
Hello.
I just wanted to know the tool or the software which you are using for all this presentation, especially for drawing graphs.
So drawing graphs, we are using the LaTeX only.
Okay. Okay, sir.
Okay.
Thank you.
So anyone else with the question?
Rajesh, there is one question in the chat also.
Okay, in the chat.
Yes,
What
please.
is the question, ma'am? I cannot find the question. If you can ask. Sir, there is one question. Is it possible to find metric like bond angle, bond length from the graph itself?
What I don't remember. What is that?
Is it possible to find metric like bond angle, bond length from the graph itself?
No, I don't know. I have not heard about.
Oh.
I don't know.
So there is one Dr. Chetna, I think. Yes. Okay, she has now lower her hand. So I think, sir, there are no more questions. Yeah. So thank you, sir, for such a nice and lovely introduction to graph labeling and its applications. Thank you, sir.
Thank you very much. Thanks a lot.
Thank you. Okay, so next lecture we have from Professor Paulraj Joseph. He is a professor and head in Manomanian Sundaran University. So he will continue with his yesterday's lecture. Please, Professor Paulraj Joseph.
Yes.
Hello, sir.
Please give me the sharing screen option.
Sir, you will get at the bottom. We can see your.
Yeah, that's what. You remove this one. Okay.
Okay, so we can see your screen, sir, Professor Paulraj Joseph.
Yeah. I am coming to the file.
Okay.
Is it clear?
Yes, sir. You can enter Control plus L key to make it full screen, sir.
Is it fine?
Sir, you can enter Control plus L key on your laptop. Control plus L.
Control L.
Simultaneously. Control plus L. Yes, now it is fine.
Okay, thank you.
Sir, you pressed it again.
Are you hearing me?
You press the key again, sir. So that's why it has gone back to the normal mode.
What do you mean?
Sir, you have to press Control plus L. It is back to the normal mode. You have pressed again. Only once you have to press. Yes, now it is fine.
Okay. Good afternoon to all. Yesterday we were talking about the Nordus-Gordon theorem and a similar result of that for domination theory due to Jagger and Payan. Today we are going to concentrate on the specific derived graphs with which we are going to get some results. So derived graphs yesterday, as I told you, so complementary graph is a graph which is derived from the original graph. Likewise, several graphs can be obtained from the given graph. For example, line graph. So it is a well-studied concept, okay, in which the given graph G, the edges are taken as the vertices. And I give the definition. The line graph LG of a graph is a graph whose vertices are the edges of elements of G, EG, and two vertices are adjacent, different only if the corresponding edges are adjacent in G. Okay. So that is, if you look at this graph, G, so the edges are labeled E1, E2, E3, E4, E5, like that. This is the given graph G. And we go to mark the edges as vertices, E1, E2, E3, E4, E5. And what are the adjacencies? This edge E1 is adjacent to E2, E3, and E2. This E1 is adjacent to E2, E3, and E2. Okay, so this is such. And we see that in this way we can see the adjacency for all the vertices, edges which are here as vertices. And the simple observation is that the number of vertices in the line graph is the number of edges of G. That is, if we denote the graph G by an n comma m graph, where n is the order of the graph and the m is the number of edges, then the number of vertices in LG is m. If that notation we will follow. Now we are going to study about the domination number for this LG. And we are going to add this with the domination number of G, and we try to get the lower and upper bounds for the sum. For the time being, we don't concentrate on the product, say gamma G into gamma L. When we talk about the domination number of this line graph, that is gamma of LG, that is an existing concept that is known as domination number. Even without the LG, we already have the concept of edge domination that was introduced by Mitchell and Hedden. That is, to take a subset of the edge set, S dash, it is called an edge dominating set of G. If every edge not in S dash is adjacent to some edge in S. Similar to the vertex domination, this edge domination is defined. And among this edge dominating set, take the smallest set and take the cardinality, and that is called the edge domination number, that is denoted by the gamma dash. Okay, always. The minimum cardinality taken over all edge dominating sets. Okay. Now we observe that the line graph is nothing but the vertices which are edges of the graph G. Therefore, the edge domination number of the graph is equal to the domination of the is the same as the edge domination number of the graph. This edge domination number has already been studied, and we are making use of this for our result. So this is the first result we have for any connected graph G of size m. What is gamma dash of G equal to? One if and only if delta dash equal to m minus 1, where delta dash is the maximal degree edge degree. Edge degree means if E equal to UV is an edge, then degree of the edge E is degree of U plus degree of E minus 2. That is the edge degree. So consider all the edges and their degrees and take the maximum. That is called delta dash. Okay. This gives a characterization for the graph with gamma dash G equal to 1. The next thing is the corollary. What will happen if we consider the T? Then gamma dash t equal to 1 if and only if t is either a star or a bistar. Bistar means an edge with the pendant vertices on both sides of the edge. That is bistar. So this characterization we have gamma dash t equal to 1. The next result is for gamma dash t equal to 2. So here we usually consider only connected graph. That is 2 if and only if there exists two edges E1 and E2 such that the vertex deleters of the ends of the edges, that is u comma v comma w comma x, if they are removed, then we get an empty graph. Of course, this is the direct consequence of the definition of minimum edge denominating set. That is, the resulting graph should not have any edges, so that all these things are dominated by these two edges uv and wx. So another observation lemma: if H is a subgraph of G, then gamma dash G less than or equal to gamma dash H plus gamma dash of E minus E of H. You take any subgraph, it has a edge denominating set. And other than that, you take E minus E, that also has a edge denominating set. Together, if you take, then that will be a edge denominating set of G. And by definition of minimum cardinality, gamma dash G less than or equal to this sum. Now look at this corona of the cycle Ck dot K1. So where K1, that every vertex in the cycle is attached to a corresponding vertex, isolated vertex, that is Ck dot K1. This is the famous corona that we are now talking about. So for that, the gamma dash is K by 2 if K is C1. If the cycle is C1, then it is K by 2. Otherwise, it is K plus 1 by 2. It is all. Now consider this corona graph for H dot K1, where H is any connected graph. Then gamma dash G equal to, wait a minute. Then gamma dash G equal to n by 2 minus 1, if and only if H is either C3 or a star. So this is for gamma dash G equal to n by 2 minus 1. Characteristics. Now we have another lemma. If T is isomorphic to the corona graph H dot K1, then gamma dash G equal to n by 2 minus 2. If gamma dash G equal to n by 2, in the previous case it is n by 2 minus 1. Now we have gamma dash G equal to n by 2 minus 2. Then diameter of H is less than or equal to 4. That result also we are getting to prove our next theorem. Another interesting lemma for the same connected graph H and H dot K1, gamma dash G equal to n minus 4 by 2, if and only if beta 1 H, that is the edge independent number of H is 2. Okay. So that is the characterization for gamma dash G equal to n minus 4 by 2. Now we are going to take the sum, bounds for on the sum. That means gamma G plus gamma of LG, we are going to see. If G is the character graph of order n, then gamma G plus gamma LG lies between 2 and n plus 1. Right, it is. Yeah, it is n plus 1. Then the lower bound, you look at the result. Look at the lower bound, that is not very interesting because it is 2. Well, one must be at least one. This must be at least one, and gamma L must be at least one. That is obvious. Therefore, it is adding greater than or equal to. But less than or equal to n is something different because line graph has m vertices. Therefore, maximum that domination number may be equal up to m, because we know that for any graph G, gamma G is less than or equal to n. But here, in that argument, we can say that gamma G may be up to m. But the result shows that even then, if you add these two, you will be getting less than or equal to n. Okay. So that result is significant in that sense. The lower bound is attained, depend only delta equal to n minus 1. That is gamma G must be 1. That is the criterion for delta G equal to n minus 1. For the next thing also, gamma LG must be 1, and that is equal to delta dash G equal to n minus. That we saw in the previous slides. Gamma dash G equal to 1, depend only delta dash G equal to n minus 1. Now the upper bound is attained if and only if G is isomorphic to C4. That is gamma G plus gamma LG equal to n, if and only if G is isomorphic to C4. Now we are coming to the another result. So up to n, it is okay. Then what will happen if we come down by 1? That is n minus 1. If the sum is equal to n minus 1, what is the characterization? Let G be a connected graph of order n greater than or equal to 4. Then the sum equal to n minus 1, if and only if G is isomorphic to A3 or C3 dot K1 or K1 comma n by 2 minus 1 dot K1. Where this dot denotes the corona of the graph. Okay. So that is a characterization for n minus 1. Now look at these graphs. So these graphs are almost all the graphs have 7 vertices. This is 7 vertices. This is 7 except this is 4 vertices. 7, 7, and these are all 5 vertices. Of course, odd, and this is 3 odd. Yeah, only this thing is even. Okay. So we call these graphs as family A, this as family B, because these are all graphs. When we saw yesterday that gamma G for any graph is less than or equal to n by 2. That is integral part of n by 2. Then if n is even, then there is a characterization. Okay. That is gamma G equal to n by 2 if and only G is isomorphic to C4 or Cn dot K1. Okay. So that is the or H dot K1 where H is any connected graph. So that is the characterization for gamma G equal to n by 2 when n is even. What will happen when n is odd? It is a very big problem. So that is characterization of graphs with gamma equal to n minus 1 by 2. Then n is odd. Leads to a very big theorem. And there the authors proved that considered some families of graphs, G1, G2, like that. Now this family A and union B, they also all look at this for all these graphs. It is the domination number is for this figure is C7. This domination number is n minus 1 by 2. So you can take this vertex, one dominating set, and this another dominating set. Okay. Then this is okay, like that. And here also you can have 5 vertices, and the domination number is 2. Therefore, it is 1 is 2, n minus 1 by 2, 5 minus 1 by 2. So these are all graphs for which these are not the only graphs, but this is the class of graphs for which gamma G equal to n minus 1 by 2. Okay. So that we denote it by script G because already there are G1 and G3, G4, G5 up to G6. I am not going to into that in detail. This is relevant for our purpose. So we consider the A union B minus C4 as the class of graphs as script G. Okay. With this background, now we are going to study about the sum equal to n minus 1 if and only if. Let G be a connected graph of order, then gamma G plus L gamma LG equal to n minus 1 if and only G is any one of the graphs mentioned above or isomorphic to S, K. S means subdivision. Subdivision of the complete graph K1, n minus. So n is odd, therefore n minus 1 is an integer, therefore K1, n. Consider this star and start dividing. That is the subdivision graph. C3, K or C4, K. C3, K. I think it is given in the next in this thing. Where C3, K is the graph obtained from C3 and K greater than or equal to that is of copies of K2 by joining one end of each K2 with the fixed vertex of C3. A vertex of C3 is identified with the center of the star, that is C3, and another graph is C4, K. This means graph obtained from C4 by joining any vertex of C4 with the center of a subdivision graph S K1, so take C4 and another copy of S K1, K, K1, K as a center, and the center and any vertex of C4 is joined by a line, that is C4, K. So that is what it is mentioned there. C3, C4K are one of the graphs G1, G2, G3 given in figure. What is this G1, G2, G3? We are giving in the next figure. So this is the graph G1. G1 is this graph, G2, G3. Okay, so these are graphs satisfying gamma G plus gamma LG equal to n minus. Okay. Now we come to the next stage. Already where the sum is equal to gamma G plus gamma LG equal to n minus 2, we come to the next level. For tree we consider and the tree of odd order. Okay. So for this tree, the sum equal to n minus 2 if and only G is isomorphic to one of the following graphs F1, F2, F9 given in the next figure. So you look at this figure. These are the only trees satisfying gamma G plus gamma LG equal to n. So it is not an easy one, or it is not too difficult. Anyhow, it is a substantial. These graphs are the only trees for which this sum equal to n minus. The next, now we are going to characterize recyclic graphs for which the sum equal to n minus 2. Let G be a connected unicyclic graph. Unicyclic graph means a graph with just one cycle, and the number of edges, that is m equal to n in that case. Let G be a connected unicyclic graph of odd order, then gamma G plus gamma LG equal to n minus 2 if and only if G is isomorphic to one of the graphs, some 29 graphs which are given in the next figure. So this is G1, G2, G20. Sorry. Okay. Unicyclic graphs G1, G2, etc. If it is going outside the screen, let me minimize it to some extent, possible extent. And this is G6, G13 up to G16, then G17, and up to G29. So these are the unicyclic graphs satisfying gamma G plus gamma LG equal to n minus 2. Now we come to characteristics of regular graphs, for which the sum equal to n minus 2. Characterization of regular graphs for which the sum equal to n. If these are connected 4 regular graph of order n, we have a lemma that gamma g equal to 3. That one simple result we have, and we are going to make use of it for the next result. That is, let G be a connected k regular graph of order n, then the sum equal to n minus 2 if and only G is isomorphic to either k5 or k6 or k44 or any one of the graphs f1, f2 given in the next figure. We look at these 2 graphs. Okay. These are all 4 regular graphs on 8 vertices. On seeing that, you may have a doubt that whether they are isomorphic or not. Isn't it? Okay. So 4 regular and 8 vertices. But you can see that they are not isomorphic by explaining a property that these 3 vertices are non-adjacent. Okay. Here there are 3 non-adjacent vertices. Okay. There is no such 3 non-adjacent vertices. If you try to take these 3, okay, if I could take these 3, then here adjacent is there. They are not mutually non-adjacent. Okay. So therefore, here only independent number is 3, where here independent number is 2. Therefore, these are not isomorphic. Okay. Okay, now we go to the next derived graph, total graph. Okay. So having seen about the line graphs, we come to the total graphs. So it is a super graph of the graph and the line graph because it contains both. The definition of total graph is the total graph I enlarge. The total graph TG of a graph is a graph whose vertex set is, we are taking the vertices and the edges as the vertex set of the total graph. And 2 distinct vertices in the total graph are adjacent. If and only if they are adjacent vertices of G, or they are adjacent edges of G, or they are vertex and an edge incident. Okay, so vertex adjacency, edge adjacency, and vertex edge incident. If all 3 conditions are satisfied, then we say that it is a total graph. For example, we give a simple example with the C3, this is the graph, and the vertices are labeled, edges are labeled. So vertices you see V1, V2, V2 is there, V3. So V1, V2 is there as a subgraph. Okay. And similarly, E1, E2, E3. We have marked here E1, E2, E3. This E1, E2, E3 is also sitting there as a subgraph. And then edge adjacent. V1 is adjacent to E1 and V2. V1 is adjacent to V1 and V2. Also, V1 is incident with E1 and E2. So it is incident with E1 and E2, therefore these adjacent. Okay. So in this way we are getting the total graph. And you see that this graph G has only 3 vertices and 3 edges, but TG has 6 vertices and more edges. That is the important thing we have to see that it has more edges compared to G and LG. So LG is the subgraph of TG. Okay. Now we are going to find some exact values for some standard graphs, just like a star, path, cycle, bipartite graph, and a complete graph, and a corona graph. So for any star G, the total graph domination number is 1. So in the star case, you take the center vertex, and every vertex is adjacent to that vertex in G, and every edge is incident to that vertex. And every that vertex takes care of all the vertices and edges, the center vertex. Therefore, gamma TG equal to 1. Similarly, for path, we have to draw the total graph, and we see that it is 2n by pi. Roughly, it is 2n by pi, depending upon the fraction, 2n by pi, roughly. For any complete bipartite graph k m comma n, gamma is minimum of m comma n. So it is enough if you take the minimum set, say x vertices or y vertices. What is that minimum you take? And that vertices will dominate all the edges and all the vertices in the other side. Therefore, minimum is n. For any complete graph kn, gamma t kn equal to n plus 1 by 2 of the vertices. Because here in the complete graph, there are non-adjacent edges, and therefore they may not be adjacent in the total graph. Okay, so therefore, it needs more vertices and the edges to dominate. Therefore, it is n plus 1 by 2. If H is a connected graph and H is congruent, H is isomorphic, H dot K1, then gamma TG equal to n by 2. Okay. So these are all for some standard graphs. Now we go to the general graphs. Now, characterization of some classes of graphs with specific values for gamma G. So this gamma G is for ordinary domination number for the graph G. We are studying about total graphs, but in the course of characterization of the sum, we need certain values for gamma G equal to 1. We know gamma G equal to 2. What is that? Gamma G equal to 3. Gamma G equal to 4, like that. So we need that values. Therefore, we have a characterization of some class of graphs with specific values. So take a tree, gamma G equal to, if G is a tree, gamma G equal to 3, if and only if G is either. We are given some graphs here. I just explain one graph. This is P3. You look at this P3. The path on 3 vertices with vertices U1, U2, U3. At U1, we attach K1 copies of P2. At U2, we attach K2 copies of P2. And at U3, we attach K3 copies of P2. So this is P3 at the 3 vertices. Here, like that, P4. At the vertex U1, we have K1 copies of P2. At the vertex U2, we attach K2 copies of P2, like that. So similarly, if you come here, when you come to P7, we attach K1 copies of P2 at U1, and at U7 also we attach K2 copies of P2, and no other vertices. Okay, like that. Or any graphs given in P1, P2. Apart from these graphs, they may be this also. Okay. So I just reduce the size so that it comes in the screen fully. T1, T2, T6, all these trees, these are also for which the gamma equal to 3. Okay, now enlarge. Another lemma, let G be a connected unicyclic graph. Then gamma G equal to 2. In the previous case, it is 3 for a tree. Now for a unicyclic graph, it is 2 if and only if it is isomorphic to C4, C5, C6. Previous notation. At the point, at the cycle C3, U1, U2, U3, at U1 we have K1 copies of P2, at U2, like that it is there. Or any one of the graphs given in the figure as P1, P2, P3. So these are the 11 graphs, unicyclic graphs for which gamma G equal to 2. Now we come to bicyclic graphs. There are graphs with exactly 2 cycles, therefore they have n plus 1 edges. Unicyclic means n edges. Now it is bicyclic, therefore n plus 1 edges. In that case, gamma G equal to 1, if and only if G is any one of the graphs H1 given in figure 1.4. You look at this graph. So this is a bicyclic graph. So gamma g equal to 1, we know that capital delta equal to n minus 1, isn't it? So in all these graphs, you see that capital delta equal to n minus 1. It is adjacent to all the vertices. There is a vertex which is adjacent to all the vertices. There is a vertex which is adjacent to all the vertices. But it is bicyclic, and we have seen that these are the bicyclic graphs for which gamma g equal to 1. Some results on the dominance number. Now we come to the total graph domination. For any connected graph G of order n, gamma Tg, I minimize to see that. Gamma Tg lies between 1 and n minus 1. Gamma Tg lies between 1 and n minus 1. Of course, this is a surprising result because upper bound is n minus 1. Whereas that is what I told you that in Tg there are n vertices, n plus m vertices. Okay. When there are n plus m vertices and m is very large naturally, it is likely to be n plus m something or n plus m minus something, but this is n minus 1. Therefore, the upper bound is reasonably good and the bounds are sharp. So you look at this theorem. Let G be a connected graph of order n, then gamma Tg equal to, I think it is for 1. Okay. Gamma Tg equal to 1. If and only if G is isomorphic to K1, so for all other graphs it is not equal to 1, greater than that. So that is a theorem proved. Now lower upper bounds on the sum of the domination. So now we come to our main concept, gamma G plus gamma Tg. What is upper bound and lower bound? So upper bound is proved to be, lower bound is proved to be 1, and that is not very interesting because gamma G is 1 at least and gamma Tg is at least 1, therefore greater than 2. But you look at this thing, this is 1.5 times n, of course minus 1, 3n by 2 minus 1. So this bound is also considerably reasonable because for this we can have less than or equal to n by 2. And if and only if G is isomorphic to K1, n, this is, and upper bound is attained if and only if G is isomorphic to, I am unable to see that, therefore, it is if and only if G is isomorphic to K. So this is the first result for the sum and extremal graphs. Okay. Now let us go to the next step. Okay. Let G be any connected k-regular graph of even order. Then the upper bound is attained if and only if G is isomorphic to C4. Okay. So that is the for k-regular graph. Now we see that Berge gave the lower bound for the domination number in terms of order and size. That is n minus m. He told that it is n minus m is less than or equal to gamma G. So by this motivation, we also try to find what is the lower bound for gamma of Tg. And we easily prove that the lower bound for gamma Tg is n minus 1. And further, this equality holds if and only if G is a star. Now we look at this thing, the remark, some comment is necessary. When we have, that is gamma, this sum, gamma Tg plus gamma Tg, this is greater, that is 2n minus 2m. Naturally, we will go to see what will be the next level that is greater than 1, that is 2n minus 2m plus 1. Okay. There may be some graphs, but we can see that does not exist a connected graph G with gamma G plus gamma Tg equal to 2n minus 2m plus 1. So sometimes in graph it happens. So for example, if you take this graph Okay, that can be easily observed. Now we come to planar graph notation. A graph obtained by joining any number of isolated vertices to each pendant vertex of graph G is denoted by GS. In this notation, P2S is a bista. Bista, you know, a single edge with pendant vertices on both sides. Okay. And now in this notation, we have this is P2S. For any connected graph G, gamma TG, this sum plus gamma G plus gamma TG equal to 2n minus 2m. I think is plus 2, the next level. Depend only these either a by star or P3s. Okay, that is the notation. Okay, this is another notation. Just I come to the last line. There are vertices U1, U2 in the graph G, P equal to U1, U2. Then what is G? This notation. At the vertex U1, I attach N2 copies of P2. At the vertex, in the same vertex, I attach N3 copies of P3. That means the pendant vertices of P3. Or in other words, vertex of DD1 is attached at U1. So N2 copies of P2, N3 copies of P3, then N4 copies of P4, like that. So that's the paths are end vertices of the paths are attached at U1. End vertices of the paths are attached with U2. Maybe paths of length 2, paths of length 1, paths of length 2, etc. P2, P3. So this is the general notation. Now this result. For any connected graph, the sum equal to 2n minus 2m plus 2 if and only if either G is C3 or P4S or C3 at the point U1, we attach K1 copies of. So in this way, this is for a connected graph, gamma T equal to the next level, I think. 2n minus 2m plus 4. The previous slide is for 2n minus 2m plus 3. Now this is for 2m plus 4. The next 3 is 2n minus 2m plus 5. So like that, these graphs are characterized, okay, for this 2n minus 2m plus 4. Now we come to subdivision graph. Subdivision graph goes some fast. It is the graph obtained by subdividing each edge of G exactly once, and we denote it by S. So look at this. This is the graph G and subdivision. Any vertex is put on a vertex, or in other words, every edge is replaced by a path of length 2. That is, for example, this is V4, V5. The edge of the single edge is replaced by a path of length 2. In other words, this is the new vertex that we call is the subdivided. Okay, some results on the domination or subdivision graph. So let G be a connected graph of order n, then gamma SG equal to 1 if and only if G is isomorphic to K2. So for path it is 2n minus 1 by 3. SG equal to gamma SG equal to 2 if and only if G is isomorphic to P3 or C3. If a tree is of diameter 4, then gamma SG equal to n minus 2. If we take connected graph, then gamma SG equal to 3, if and only if it is isomorphic to P4, P5, K1, 3, C4, K5, K5 minus 4, etc. or any one of the graphs given in the figure. So this is H1 and H, gamma SG equal. Because these simple results are used for the sum. Now bounds for the sum, gamma G plus gamma SG is less than or equal to 3n by 2 minus 1. Lower bound is 2. And lower bound is attained if and only if G is isomorphic to K2, and upper bound is attained if and only if G is isomorphic to C4 or Kn by 2 minus 1. Now this is gamma SG plus, we have talked about 3n by 2 minus 1. Now this is, it is a character graph of order n, then this sum, we start from the lower bound, greater than or equal to 2, therefore we go to the next level, greater than or equal to, what is equal to 3? Then we have proved that it is isomorphic to P3 or C3. Okay. Similarly, gamma SG plus gamma G equal to 4 if and only it is isomorphic to any one of the graphs or the H2, where H2 C5 dot A1 or one of the graphs in figure, even in the next figure. Okay, you look at this thing. This is connected graphs of even order, and this gamma SG plus gamma G equal to 3n by 2 minus 2. Upper bound equality. Of course, less 1. Now, characterization of k-regular graphs. Lower bound. Let us take a connected graph. Lower bound we have gamma SG greater than or equal to n minus m, as Bergy has already pointed out, and that is true for line graph, total graph, and for this graph also. And equality holds if and only p equal to k2. For any connected graph, if you take the sum, it will be greater than or equal to, because of this n minus m, that is also n minus m, therefore 2 times n minus m, like that. Now we find what is that. Gamma G plus equal to n plus 2m plus 2, if and only G is isomorphic to k1 comma 3. And that is for characterization plus 2, characterization for plus 3, like that it goes on. Now this is for plus 4. And either these graphs or these graphs. All are characterized. Now we come to power graphs. I go fast. So power graph means it is the graph G power k, means k is an integer. Then the graph with the same vertex set. And adjacency is that set of all the vertices which are at a distance less than or equal to k are made adjacent. Okay. So u and v are at a distance 2 means they are joined in the case of G power 2. If u and v are at a distance 3, if we talk about G power 3, then they are made adjacent. Okay. So G square is the square graph, shortly speaking. If you look at this G square. So these vertices and these vertices are adjacent. So that is given at a distance 2. And these and these are adjacent, and that is given here. And this vertices is adjacent to this vertex. I think it is drawn, it is not drawn here, but it has to be. It has to be here. This has to be adjacent. Like that. And if you come to here, vertices at the distance 3 are also made adjacent. 1, 2, 3. So 1, 2, 3. So this and this are adjacent. So you see that G is a subgraph of this thing, and G square is a subgraph of the G power 3. In that way, we have the chain of subset. Okay. For any connected graph G of even order, gamma G square is less than or equal to, we have found an upper bound for gamma G square n minus 2 by 2, and equality holds if and only P6. So this type of results will be going on. I go fast. Then the next level, n minus 1. What is that? Gamma G plus gamma G square less than equal to n minus 1 if and only C4 or P4. Now, if it is odd order, it is n minus 1 if and only we have the result. Similarly, G is a connected graph of odd order, then it is equal to n minus 2 if and only if G is isomorphic to P5, P7, or any one of the graphs. I think I have given you the family of graphs A union B, in that B only C3 was there, and you remove that, all other C5 cases, and that is the graphs for which the sum equal to n minus 2. So bounds in terms of order and size. Okay, gamma G square greater than or equal to, there is a Bergy type result, gamma G square greater than or equal to n minus m, and we go fast. And if you add them, it will be greater than or equal to twice, and you can talk about 2n plus 2n minus 2m cases, and like that. So it is 2n minus 2m plus 1. In the previous list, I think you can see that 2n minus 2m plus 1 dependent on G is either a by star or P3s. So this is for 2n minus 2m plus 2. Now look at the planar graphs. You know the definition of planar graph. It can be drawn in the plane so that edges intersect only at the ends. So for if G is a planar graph with the diameter G equal to 2, then gamma G plus gamma G square less than or equal to that bound is 4. You see the planar graph P of diameter 2 with the domination number 3 for this graph. Okay, let us, that is a special situation where that planar graph plays a role. Therefore, we avoid that planar graph P, and if all other graphs of diameter 2, then the sum is less than or equal to 3, and the equality holds for regular graphs depend only if G is isomorphic. Now, this is for less than or equal to 3. These graphs are given are characteristics. Equality for the upper bound equal to 3. Now, lastly, we come to block graphs. So, block graph means the blocks in the graphs are taken as vertices, and the 2 blocks are adjacent. 2 vertices are adjacent if the corresponding blocks have a common cut vertex. For example, if you take this graph, so this is a block, this is a block, this is a block, this is a block. We have marked them B1, B2, B3, B4, and join them if the corresponding blocks have a common vertex. This have a common vertex like that. This is a block graph. Now we have to study about gamma G plus gamma of this DG. Okay. So simple observation is gamma of DG less than or equal to gamma G, and some more observations are there. So the domination number of the line graph that already we have seen. If G is a 3, then LG is isomorphic to block graph because every edge in a tree is a block. If G is a k-regular graph of order 8, then gamma G equal to 2 or k equal to 4. All regular graphs of order 8 are blocks. There are exactly 2 to 4 regular graphs of order 7, and both of them are blocks. Okay, then domination number for block graph. We have this lower and upper bound, gamma BG less than or equal to n minus 1. Okay, calculation of k-regular graphs and the sum also. And look at the sum, that is an Nadas-Gardam type sum, gamma G plus gamma BG less than or equal to bounded by n minus 1. And the upper bound is attained if and only. Okay. Characterization of k-regular graphs. If G is a connected k-regular graph, then gamma G plus gamma G, BG equal to n minus 1 depend only if G is isomorphic to K. So this is for the next level. I think it is for n minus, that is for n minus 2, this is for n minus 3. These are the characteristics given C6 or C6 bar K33 or K5. Okay, now this lecture we have seen 5 types of derived graphs. One is line graph, total graph, subdivision graph, hover graph, and block graphs. And these are all derived from the original graph. Therefore, we have given the title as derived graph. Now, this lecture is based on the recently submitted PhD thesis by my candidate, Murugan. It was awarded recently. And the papers have been published there. Now, if you look at this thing, look at this reference by a study on induced cycle path number of graphs. Yesterday, I told you that I come to the open problem. I think it is open problem. Okay. I recall the open problem. It is not included in this. Okay. Yesterday, I told you that if alpha G is any graph parameter and alpha G plus alpha G bar, people study. And what we suggested is alpha G plus alpha of derived graph G. If DG denotes the derived graph. So complement is a derived graph. Subdivision graph is a defined graph. What we have already seen, all these things are derived graphs. Okay, and you can take any concept. You can take any concept. For example, two of my students have taken the concept resolving number of graphs. Okay, resolving number, just like domination number, resolving number is defined, and she studied about total resolving number denoted by PR of G. Okay, and that the concept is different. Total resolving number, and for this total resolving number, she studied for the derived graphs, for the various derived graphs, and that was enough for her to get a PhD in the year 2000. I think it is 90. And another student, he studied about induced path number that was introduced by, I think, that and it is induced path number. That is nothing but partition of the vertex, minimum order of the partition of the vertex such that the induced sets, the vertex induced subgraphs are nothing but paths. That is path partition number. And she developed a new concept called cycle path number, that is rho CP. And thus she obtained a new parameter. And for that, she studied the parameter not only with respect to complete graph, that is complement graph, but also with respect to all these type of derived graphs. Okay. Therefore, I wanted to type that open problems here, but unfortunately missing. Okay. Okay. So totally, 3 theses have been awarded on this topic. That is not the atom type results for derived graph. Maybe in domination theory or any graph theoretic parameter. For example, we have a covering number, independence number. Based on this thing, we can study about what is alpha of G. Alpha is a covering number of G, then alpha G plus alpha of T. Total. Nobody has studied so far. What is alpha G plus alpha T? Like that, alpha G plus alpha SG. So all these things are proven. You can either change the parameter or you can change the derived graph. So in that way, you will get so many combinations of cases, and that will lead to a variety of problems, which is a new direction in this field of research. Okay, I think with these few words, I request the audience to go through the reference 1. Yesterday I told you, if you go through this first reference, then only you will be able to understand what is the importance of this lecture, because you have 80 pages of this survey only for G bar, G and G bar, nothing else. Okay, we can look them in a different angle. That is why I have given this. Okay. So some references are given here. Okay. If there is any question, I'll be happy to.
Yes, sir, there are 2 participants who have raised their hands. So
Okay.
if any participants have any question, they can raise their hand. I will take the question one by one. So Malathi, you can ask your question. You can unmute yourself and ask your question.
So good afternoon, sir.
Good
Sir,
afternoon.
I'm Malti. I'm doing my research in spectral graph theory, and particularly I chose Nordas-Ghatan type relations on eigenvalues and eigenvectors of spectral radius and also signless Laplacian spectral radius, and
Very good.
on G and G complement, sir. Now only I was able to see that you applied Nordas-Ghatan type relations on derived graphs like line graph, total graph and all, sir. But I have one doubt in this also. How is a regular graph a derived one?
Regular graph is not a derived graph. What we have considered is, if G is a regular graph, okay, then what is gamma G plus gamma LG like that, or gamma G plus gamma T? Regular graph is not a derived one.
Okay, okay,
It is
sir.
the original graph. Every
Okay.
vertex is empty. You
Okay,
can
sir.
also derive, you cannot derive regular graph from any other graph. Okay, it is not the case.
Okay, sir.
It is not a derived graph.
Okay, sir. So till now I was working only with the G and G complement and was getting bounds on that only, sir, like upper bound and lower bound, and the condition for applying that Nodus datum and getting a, lower bound and upper bound, and sum and the product of the sum and the product is also is there in the Nodus datum.
Interesting. It's also interesting. Yeah.
Yes, sir.
Yeah.
I have a
Now,
doubt.
varieties of parameters.
Yes, sir. In case while I am presenting my Viva, the one question they may ask, what is the application of a Nodus datum? Why do you apply that? Like that, they ask. I'm not able to get the reference.
You see, it is a general question asked everywhere. Okay, we cannot find applications for each and everything. I mean, so graph theory is application-oriented subject, and domination also, labeling also, decomposition also, we can say application. But for each and every result, what is the application for that? That is maybe a silly question. Okay, I may be pardoned to say. It is a general question they are asking. Okay.
Yes. Because sir, our DC member all belonging to computer science department.
Yeah, that is why they will be asking about applications.
What is the application? Like that they are asking, sir.
That is just we can repeat saying that generally it is application oriented subject. Each and every result need not have an application, not just. So they try to solve the 4-color conjecture. At that time, they attempt to do several results. They study about the chromatic number of G and G bar, how it will be helpful. As a byproduct, they got the result, So, like that, we are following that. Okay.
But results are very much interesting and very fascinating, sir, in this the Nodus setup type of relations. And okay, sir. Maybe I just want to know all the literature regarding the Nodus datum type papers.
First reference you can get it from the net. Discrete applied mathematics. It is published in that journal. First result you see a survey of Nodus datum type relation. Discrete applied mathematics. Okay. And if you send a mail,
yes, sir. I'll definitely
mail, and I will forward. I have in my laptop.
Okay, sir. Okay, sir. Okay, thank you, sir. Thank you so much.
So next, please.
Okay, next we have this Anjan. She can ask her question.
Dr. Rajesh, I want to ask one question.
Okay, ma'am, please.
Yeah, please. Welcome.
Yes, Professor Joseph. So since you have been talking about the domination number gamma G, so have you also looked into the independent domination number of these graphs? And can we say that the domination number of the line graph is the domination number of line graph always equal to the independent domination number of the same line graph? And the total graph and the subdivision graph. So how about the line graph? For the line graph, is it not always true? Do we have an example? Do we have an example in which for a graph G, the domination number of LG is not equal to its independent domination number? Do we have? Yes.
That is possible. I think it is possible.
Is that possible?
Independent domination number, isn't it? Gamma I.
No, and as regarding subdivision graphs, same question. My same question is there. And regarding total graph,
you say that independent domination equal to
independent domination number equal to the domination number.
I think it is possible in the case of K13 graph, If the graph is K1 comma 3, 3,
Yes,
then gamma I equal to gamma.
gamma equal to gamma.
Yeah, yeah. That the criteria is if G is K1 3, that is star K1 comma 3, then should not be there as an induced subgraph.
So I think
That
it will
is
be
called
interesting.
K1 comma 3, 3.
No, I understand, but I think it will be an interesting study that for which derived graphs the domination number equals its independent domination number, because as it is this equality, it's a fundamental problem
Yeah,
for
yeah, yeah.
applying such
That is
graphs.
also another direction. Yeah, yeah. Yeah, yeah. For which graphs domination number equal to independent domination number.
So,
Okay.
I think for several derived graphs, it will
that is
induce a
also,
good
that
research.
is also another direction. Interesting.
Yes.
Yeah.
Yes, and similarly, your this goddess Nadam type results, we can also think of gamma I things, independent domination instead of only domination.
Yeah, yeah. Yeah, gamma Ig plus gamma of any derived graph.
Yes,
Okay.
yes.
So here,
So I
for
think
example,
I
have
think we
given
can.
five derived graphs.
Yes, we can work on these.
In the literature, you may come across any type of derived graphs. For example, H
Yes.
dot K1 itself is a derived graph,
Yes. Thank you so much. Thank you.
Thank you.
Okay, so Anjan, now you can ask your question.
Hello, good afternoon, sir.
Hello,
Sir,
good afternoon, welcome.
Sir, I have doubt on one of your slides, sir, slide number 23, sir.
Slide
Sir,
number
actually,
23.
sir, 23, yes, sir. Sir, can we see, sir?
Okay. 23.
Sir, it is 17. You have to go down a little bit. Total graphs, maybe. Total graphs, sir. Total graphs.
In the topic total graph?
Click on the total
No,
graph.
sir, about the domination number as a 3, sir, you have shown the figure. Sir, about the domination number.
This page is 19, sir. Please go a little below, sir. Drive.
You can
go by navigation. Page number is 19, sir.
You can scroll.
Exact value for some standard graph, I think.
It is not moving. I am going forward. Isn't it? I have to go backward.
Sir, forward, sir. Forward, sir. Forward.
Forward, sir. Forward.
Onward.
Sir, forward, sir. Sir, 21, 22. So one more. Sir, this one, back one, sir. Previous one, sir. More previous, sir.
Back, sir. Back.
Back, sir. Back. Sir, one more, sir. It's 26, sir. Sir, I want 23, sir.
Where's the
So
number?
one more. One more, sir. One
more forward.
One more, sir.
Backward,
One more
sir.
back. Backward, sir. Yes, sir. One more, sir. Yes, this one, sir. Particularly. No, sir. Figure one, previous.
This is
Forward. Figure 1 forward, na?
So yes, sir. Figure one, sir. 22, 23, sir. Next.
One forward, sir.
One. Yeah, this one, sir.
Back, sir. Figure.
What is
Back. One back, sir.
This
figure.
one.
what do you want? Is it right?
No, sir. Figure one, sir. That you have
Below.
T1, T2, T3, T4, T5, T6. No.
Yeah. Is it okay?
Okay. So next one, sir. Figures, sir. Sir, in this, sir.
This one.
So how the domination number of T4, T5, T6 are, sir, 3, sir.
Yeah. These are graphs for which domination number is 3. Do you have any doubt?
Yes, sir. Sir, how, sir, T6 having the domination number
T6.
3?
Not T6, you say.
Yes, sir.
This is if you take this vertex.
Yes, sir.
It will dominate this thing. And if you take this thing, and this is missing. Take
T4 also, T5 also, sir. One vertex is missing each, sir. In T6, 2 vertex missing.
T5
Yes, sir.
and T6.
Polraj, for T5 and T6, gamma G is not 3.
Yeah.
Even T4 also,
Incorrectly
sir.
written.
T4 also, sir.
This is 1.
Yeah, correct. T4 also.
Yeah.
It is wrongly written. It has to be corrected.
Okay, sir. That much only, sir.
Yeah, we will take it the drawing of the graph. Okay. And I will
Okay. Thank you. Thank you, sir.
Thank you.
Thank you, sir. Thank you.
The next we have Santanara. So yes, please ask your question, Santanara.
Yes, sir. Sir, I'm very much
Anybody else?
interested. Yes, sir. Good afternoon, sir. I'm very much interested about your work, sir. And
Okay,
I'm
thank you.
assistant professor as well as new researcher just now.
Okay.
PhD. I have planned to start research in labeling, sir, but I'm new
Okay.
to dominating. But one thing, the larger graph, for example, vertices more than 20, something like that, how do I find out the domination number? Suppose I find some number, how do I check whether that number is correct or not, sir?
That is, we have to go by the algorithms for that.
Is there-
we
is
have
there
to
any-
usually.
Is there any algorithm?
What we take is vertex of, yeah, there are several algorithms, but for general graph it is difficult. For general graph, the algorithm does not work. It is still determination of domination number gamma g for larger graph is an NP complete problem. Okay. For trees or smaller graphs like that, we have algorithms that is polynomial time algorithm. Or like a bigger graph, this algorithm is not always working. It is NP complete. Okay, that is approved there.
Okay, sir. And one more doubt, sir. That you have told corollary for any tree of order n, gamma dash of t equal to 1 if and only if t is either star or bistar. And so many theorems you have showed, sir. But
Gamma dash g. Yeah, gamma dash g. You take a star. You take a star. You take any edge.
Okay, sir.
And that is a dominating, isn't it?
Okay, sir. And if I add or remove from that graph, whether it may be definitely change, sir, or maybe remains, sir.
Which one you are removing?
Removing an edge or add one edge. Suppose in that case, whether it will be.
Remove one edge. How do you add?
By duplicating one edge by vertex, something like that.
No. That is not possible because only for a star and bistar it is one. Okay. And if you remove one edge and then duplicate, then there may be a cycle, isn't it?
Okay, sir. Okay, sir.
Then it will not work.
Okay, sir. You have showed a larger number of results. Are you proved that all these things are how the proof, the way of proof is induction by path?
Yeah. That is why, in some places we were giving that gamma dash of g equal to 1, gamma dash of g2 equal to 2, 3, like that. Okay. Some small results we are saying. Okay. That is, of course, easily we can get. Then when we go for the some say gamma g plus gamma of tg, gamma of lg. Okay. And the gamma g number will be used. Gamma dash g will be 1, 2, 3 we have counted. And that will be used so that we will be getting we will be able to fix the graph in such a way that because we have given some lemmas, for 1, 2, 3, etc. They will be useful to tackle the sum. Okay, because it will be gamma g will be taking one part and gamma lg will be taking another part. So one of them will be 1 or 2 or 3, then the other will be more, like that. So in this way, we have to compare these two things and come to a conclusion that this is the fixed graph.
Okay. Okay, sir. Thank you very much, sir.
Okay.
The next question is
Professor Rajesh, I want to ask. Professor Joseph,
yeah, welcome.
Can we relate this to the diameter of the graph? Because does it say that if the domination number is 2 for a unicyclic graph, then should we say that diameter of the graph must be less than or equal to 4? Is that correct?
Okay. Can you, which slide, have you noted that, please?
No, slide is before me. Slide is before me. So the same slide which was being talked about. So looking at the graphs, looking at the graphs, we can conclude as a remark that if this happens, then we can relate it in terms of the diameter of the graph. That's what I'm saying.
See, later we will be coming across to say that if gamma dash is something like that.
No, no,
then
no. I'm
diameter-
saying gamma G. Same slide. I'm talking. Same slide. That is gamma is equal to 2. Same slide which the previous this participant was asking.
Like same slide 21, isn't it?
23 slide number, sir. You have to go back.
Yeah, I am going back.
Same figure, that T4, T5, T6. Yeah, this one.
Yes, this one. Yes. Next. No, the figures.
One more, sir. One more. Yeah, this one.
Yes, this one.
Back, sir,
So,
back.
G1, G2, G11.
Next.
No,
Figures.
sir, back. You have to take one back. Yes, this one.
Yes.
Is it this?
So my question is that if gamma G equal to 2, then for a unicyclic graph, so this implies diameter of the graph is less than or equal to 4. Is that correct? Or what is the maximum diameter? You can raise this question.
Domination 2 means, for example,
What is
you take P6, you take the graph P6, pass on 6 pieces.
No, but in this, what you are showing, I am seeing only
This
this.
is unicyclic graphs, you know. This
Yes.
result is for unicyclic graphs.
No, I agree. I am asking only for unicyclic graphs.
You are asking about?
Unicyclic graphs only.
Yeah, unicyclic graphs for which gamma G equal to 2 if this thing or these graphs. Am I getting?
Yes.
Diameter is less than or equal to maybe 4 or 5. We have to say. But we have fully characterized, you know. Sorry, it is jumping.
Professor Joseph.
Yeah.
This is. Can you hear me, Professor Joseph?
You see, here this is.
Good afternoon, Professor Joseph.
I think maximum diameter 5. 1, 2, 3, 4, 5. Maximum diameter less than or equal to 5.
Yes. Correct.
Correct. It is less than or equal to 5. But if it is not unicyclic, you see that if you take P6.
Yes.
Pass on 6 pieces.
Yeah, it changes. Yes.
Like
Okay. Thank you so much. Thank you.
Okay, sir. So we have next question from Dr. Gajendra.
Professor Joseph, good afternoon.
Good afternoon.
And thank you, very informative talk. I have a very small question. Can we define the total product for the digraph, sir?
Total graph for the?
Digraph, directed graph, sir.
Total graph for the digraph, you see, digraph means there is a direction, you know. Digraph means the graph edges are directed edges.
Directed edges.
If it is, we can have the corresponding total graph, and now we are giving the direction. We have to make a set of rules. Okay, if this is oriented in this way, and then how the new edges will be given orientation, we have to define. As on date, there is no directed graph for the total graph direction. We have to formulate. If at all we want to define a directed total graph.
Directed total graph. Okay.
Then I think that you mean that there is a directed graph. Am I correct, sir?
Yes, sir. Directed graph, digraph. Yes.
Yeah,
Where every edge has some kind of orientation. Yes, sir.
Okay. Digraph is there.
Yes.
Then we want to total graph. Then the vertices are also taken and edges are also taken. How the adjacency is given, you have to define according to your requirement or convenience. You have to define how the adjacency and orientation.
Okay. But
both things are important.
Okay. I'm not seeing the literature now. That means it is not defined till now, sir. Or that
I have not seen that. I think there is no such thing.
Okay, sir.
I have not come across.
Can I,
Anyhow, it is a good question because always people are tempted to go to directed side, but we have to define the concept.
can I
Thank you, sir.
give him some direction?
Hello.
Can I give him some direction? For the definition?
Some direction means some meaningful direction. You have to suppose
direction, sir.
in the.
Good afternoon, ma'am. Good afternoon, ma'am. Gajendra.
See what happens for digraphs, line digraphs are well defined.
Yes, ma'am. This is
There are
given.
lot of studies on line digraphs.
Yes,
Even
ma'am.
find line digraphs.
Yeah.
In total graphs, we have to see the directions. Adjacency will be remain as in the graphs, and we have to see the direction with respect to line as well as the vertex. That's all. One adjacency is already there. If verses corresponding to the edges, that will follow the definition of the line with respect to edges. With respect to vertices, we have to see how they are, how the two will be connected. It can be very well defined.
Whether it has already been defined, madam?
It is not, total digraph is not defined.
Not defined, ma'am. Yes.
Yeah. That's what I mean.
But line digraph are well defined and well studied also.
Yes, yes.
Because line digraph, if you take, we have taken line digraph, line sign digraphs, everything has been done, but total we have not seen. We have not, so far we have not thought about that one. I think it can be very well defined. Total digraph can be very well defined. Okay, thank you for your question.
Thank you, ma'am. Thank you, ma'am. Thank you, sir. Professor Joseph, thank you for a wonderful talk. We enjoy.
Any more questions from the participants?
It's already 1:30.
Okay.
2 o'clock, we have to take lunch.
Yes. Yes.
I have to.
If there are participants who want to ask question, then they can write to Professor Paul Raj Joseph. Okay. So thank you, sir, for such a nice talk on Nordas-Gottman type relations for derived graphs. Okay. Thank you, sir. So next session will start at 2 p.m.
Be safe.
Yes, ma'am.
I'm telling everybody, be safe.
Yes, yes.
Yeah. In the COVID-19,
yourself and your loved ones
we
safe.
wish and pray. All of you, please be safe.
So we meet at 2 p.m. now.